Okay, this is Unit 7, Day 1. This whole unit is called Polynomial Functions Notes. Day 1 is about power functions, which, don't forget, another word for a power is an exponent, so it's also about exponential functions. The little text box reads, a power function is any function of the form f of x equals a times x raised to the b power, where a and b are real numbers not equal to 0. All right, so basically example 1 here has you guys just filling out a chart. One thing I wanted to point out to you guys, please make sure you're paying attention to the difference between squaring a negative number and then taking the opposite of a negative number. So, for example, when I'm filling in this chart right here, this wants me to take the number -3 and substitute it into -3 squared, -3 cubed, -3 to the 4th power, -3 to the 5th power. So, because it's a negative number, you must use parentheses. If you do not use parentheses, what I highlighted up here tells you that they're not equal, okay? Because this one on the right means the quantity -3 squared, which means -3 times -3, which is a +9. The one on the left means take the opposite. That's what that negative sign means. Take the opposite of 3 squared. So, for example, 3 squared is 9. The opposite of 3 squared would be -9. They are not equal. So just a recap here, please make sure you don't forget to put all of those in parentheses when you are raising a negative number to a power. Okay, so I'm not going to take the time to explain how to do all this, but hopefully you can check and match your chart here. One thing I do want you to realize about this pattern right here is all even exponents result in a positive answer. Okay, so 2 and 4 both are positive. Why? Because a negative times a negative, so a pair of 2 results in a positive. So even if it was negative times negative times negative times negative, you pair up 2 of them, you get positive. You pair the other 2 up, you get positive when it's a 4th power, and then you get positive. Anytime it's an odd exponent, like 3, that's a negative times a negative times a negative. Well, I just said 2 of those negatives, negative times negative, is positive, but then when you take that product that's positive and multiply by another negative, you get another negative number. So quick recap here, if you have an even exponent or an even power, your negative result will always be positive. If you have an odd exponent or odd power, your power function will always be a negative. Okay? So, saying that, I know that these will always be negative right here, just because I'm raising negative numbers to those powers. Okay? So then this one becomes 4, 8, 16, and 32. Okay? And then 1 should make sense. -1 squared is +1. But -1 cubed will be -1, okay? Zeros all remain zeros. 1 to any power is just 1. And then the 2's take on the same pattern, so 4, 8, 16, 32. But remember, it wasn't a -2, it was a +2, so the patterns of positive and negatives don't happen. Same for 3, so it's going to be 9, 27, 81, and 243. Okay, picking up the pace a little bit. Example 2, use your calculator along with this example 1 to make a quick sketch of each power function below. All right, y equals x, you should know that. That's the diagonal line going through quadrants 1 and 3. Okay, x squared, you should know that. That's our quadratic function. It forms a parabola. And always just train your brain to label those. X cubed might be new to you, but hopefully you get, it looks like it's half of a parabola here, and then the reflection of the other half of the parabola over there. So that's y equals x cubed. Again, you can just put this on a graphing page on your calculator. Y equals x to the 4th is similar to x squared. So it's like x squared, but you're going to see it's much wider. And again, I wouldn't just copy mine. I would put it in your graphing calculator and notice how the bottom is wider. So if you notice on part B here, y equals x squared, this comes nice and smooth right into the origin, where this one has a much wider bottom. Okay, you could look at the table of values to see what the actual numbers are. They're not steadily 0 there. Please don't think that. I just kind of drew what it looks like to the eye. All right, in part E, y equals x to the 5th is very similar to x cubed, but again, wider. So in x cubed, it's nice and smooth, comes right into the origin. This one just takes a wider approach, just like before, with x to the 4th. So this is x to the 5th, and again, please put these in the graphing calculator. Ooh, that is ugly. Please put these in the graphing calculator, and you'll notice there's some wider bottoms there. Okay? Example 3. Use example 1 and 2 to answer the following. A. Which power functions are even functions, and why? What do you notice about their exponents? Okay. Our even functions are y equals x squared and y equals x to the 4th. Of course, it's x to the 6th, x to the 8th, but those aren't in examples 1 and 2. What do you notice about their exponents? It's all your even exponents. Okay, all of your even functions have even exponents. Okay, why do you think this happens? Because they are symmetric to the y-axis. Okay, so back in Unit 4, guys, you'd have to flip back to your Unit 4 notes and the transformations. We learned what an even and odd function is. And if something was symmetric to the if something was symmetric to the y-axis, we called it an even function. Okay, if it's a reflection through the y-axis, you have an opposite x, but the same exact y. So what does that mean? You change the signs of your x, but y stays exactly the same. Part B, which power functions are odd functions? Well, if you guessed, it's going to be y to the x. Remember, that has an imaginary power. Well, it's not really imaginary. We just don't write the script of to the first power. So y to the x, y equals x cubed, and y equals x to the 5th. Again, x to the 7th, x to the 9th also counts. Y, what do you notice about their exponents? They're all the odd exponents. But why are they going to be odd functions? Because they are symmetric to the origin. And if something is symmetric to the origin, we say that it is an odd function. Both signs change. So it's opposite x and opposite y, which means you're going to negate your x and negate your y. Okay, so something to pay attention to with all of those functions, if you go back to the previous example 2. Something that's in quadrant 1, it ends up in quadrant 3. It's a diagonal. If it was in quadrant 2, it's going to end up in quadrant 4. It's kind of like a rotation of 180 degrees. All right, example 4. Answer each of the following. All right, so some keywords here. If the point 2, -7 lies on the graph of a power function with an even exponent. So you need to think if it's an even exponent, it's an even function. If it's an even function, it's symmetric to the y-axis, which means you change your x but keep the same y. Okay, because it's symmetric to the y-axis. So if you look at the choices that would change your x, it would have to be a -2, but your y stays exactly the same, is going to be choice 1. Part B, if the point 27 lies on the graph of a function with an odd exponent, so if it has an odd exponent, it's an odd function. And don't forget, if it's an odd function, it's symmetric to the origin, which means you're going to change both signs. So when I go through and change both signs, it becomes -2, +7, which is choice 2. All right, moving on. End behavior. End behavior is just what it says here. An end behavior is what the values are doing at the ends. Keywords here, y values, and strictly at the ends. Now, the reason I want to have you pay attention to at the ends, because sometimes the y values will go increasing and then it'll go decreasing, but it's the very end y values that you have to pay attention to. Okay, so the first little chart here, it says, notice for examples 2 and 3, the even functions have the same end behavior and the odd functions have the same end behavior. What is it? Write your response to the table. All right, even functions like x squared, x to the 4th, you're going to notice, okay? And the easiest thing to do, guys, is to put y equals x squared in your calculator, okay? If you put that in your calculator, you get your parabola, you know what it looks like, but your table of values, okay? Your table of values here at 0, it's 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and even if you want in the negative direction, negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9, and so forth. So what you can do is, once you input this function into your graphing calculator, insert your table by Control-T, and you're going to notice, so they're asking you, as x goes to positive infinity. So look over here. These are my x values. As this is increasing to positive infinity, what is my y's doing? My y's are also going to positive infinity. Okay? And then it says, well, what happens when x goes to negative infinity? So if you look at your table of values, as my x's go more negative and more negative and more negative, what's happening to the y's? Well, the y's are just increasing on the positive side of it. So y goes to positive infinity. Okay, so that happens for all even functions. Odd functions, you can do the same thing. You could pick y equals x. That's probably the easiest one to pick. But you could put an x cubed. But a y equals x table, if you put that in your graph y equals x, it's like part A in those graphs that we just drew. But at 0, it's 0. At 1, it's 1. At 2, it's 2. Sorry about that. At 3, it's 3. At 4, it's 4, and so forth. At negative 1, it's negative 1. At negative 2, it's negative 2. So now, as x approaches, or x goes to positive infinity, your y is also going to positive infinity. So the best way to do this is to graph the function, put it in your graph page, and then insert a table, just look at the values. As x goes to negative infinity, as it approaches negative infinity, your y's are also going to negative infinity. So that's something that you're going to remember. So all even functions end up going to and having end behaviors of positive infinity. In all odd functions, it depends what the x does. If x is going to positive infinity, y is going to positive infinity. If x is going to negative infinity, y is going to negative infinity. Example 6. Use your calculator to make a sketch of each power below. All right. Again, we kind of did x cubed down here, so we're going to do that one. This is y equals x cubed. All right. If you use your graphing calculator, hopefully you guys remember, and you have to remember, it's not an option here, CBAD. Back from Unit 4, when we were doing transformations, we were doing vertical shifts left and right. I'm sorry, that wouldn't be vertical. We were doing vertical shifts up and down. We were doing horizontal shifts left and right. We reflected over the x-axis. We reflected over the y-axis. We did vertical stretches. We did vertical compressions. We did horizontal stretches. We did horizontal compressions. Okay? So hopefully you remember this. But if you just put this in your graphing calculator, that's like your A and C bad. That's a reflection over the x-axis. So this normal graph right here for y equals x cubed gets flipped over your x-axis. So this is y equals negative x cubed. Okay? So what would happen to if you throw a 3 in front? That is still like your A from CBAD, but that is a vertical shift by 3. So what happens when you, I'm sorry, not a shift, a vertical stretch. Sorry guys, there's stretches and compressions. I misspoke a second ago. Alright, so what happens? They get narrower, they get skinnier. So it gets closer to the axes. And again, the best way is to put that in your graphing calculator and put the original one in, and then you'll see how this thing is going to close up and get narrower.